All right. Hello, everyone. Welcome back. This is continuing from our previous chapter for linear regressions and moving on to chapter 4 to talk about classification model. So today what we're going to go over is how to do the logistic regression models. And we have the videos that already put up on to the class for you guys to learn about the logic of the logistic regressions. You also have the class lecture to go over the concept. So today what we're going to do is just very quickly jump into the model and see what we can do with the logistic model and how to read those outputs. All right, so in this lecture code number 4, you are going to see some extra codes here that it's not related to logistic model, but it's good for you guys to know. Not only you can retrieve those data from the library, like the ISLR library or maybe the MASS library data sets, you can actually call those library outs and also at the same time use those data and export it to your machines for later use. So for instance, we would like to see if we can bring those ISLR data sets out again. So we're going to import the library by using the require functions. Now the package is being called out, and what I'm trying to show you here is we are going to take one of the data sets from the ISLR library and trying to save it as a Excel files in your machines. So all you need to do is to install this package called XLSX. So you can actually run these installations. I have already installed it to my machine, so I don't have to run it. So after you install the package, call the libraries, and then you want to check if the dataset is available now. You can actually try to call the dataset default. And those are the names of the variables in the default dataset, including default, students, balance, and income. And now what you need to do in order to write this data to your machine is to use this function called write.xlsx. So this function allows you to write whatever the data frames or tables that you have currently work on, or maybe from the existing library, and save it to a path to your machines. And it will allow you to save it as a Excel files here in this case. So in this case, obviously we are trying to save the default data sets. If you don't know what it is, you can always ask, right? So you can actually type out the question marks default, and it will tell you this is a data set from the ISLR library. It's about the credit card default data. And I'm going to put this on the first parameter here in these functions, and then I'm going to make a comma right here. And the second parameter you have to put in is the path to where you want to save it. If you want to save this data set to your current directory, let's say you have this our files saved it on desktop, you can actually just type out the name of this files. It can be any name. It can be a default.xl. It can be like project1.xl. It could be any name you want to name it, and it will save it as the files to this name and at the current directory. If you're working on this our files on a desktop, then well, basically it will save it on the desktop. But for now, I'm going to basically say, well, I want to save this to a path here. since we are in the project folder, in this project folder, or the Gate repository folder, you have this data folder here. So that's why I call it data here. So it goes into the data folder. And within the data folder, there are two folders, textbook data and practice data. So I choose to go to the textbook data. And then I would like to save this file as default.excel. And row.name, you can define whether it's true or false. I think it's default to be true. Otherwise, I won't put false here. So it basically just tell the functions whether you want to include the rows names in the data. Save it as an Excel file. So in this case, well, you know the first row, it's not the data points. It's basically the title name. So you don't want to save that first row as your data. All right, so let's give it a try. So run this code. And as you can see, it's loading right here. So when it's finished loading, it should pop up. Okay, so now it's gone. And here you can see, well, this is the Excel file that actually being saved to the folder. And you can actually view this and see how the data looks like in Excel format. Also, it's equally important for you guys to know, well, it's not always the case you have to pull those data from a library. You can actually save those data like I did for you guys into a folder so you guys can actually use it whenever you want. All right, so having have said that enough, I think we should move on and talk about the model. Well, today in this exercise, we want to actually use the stock market data sets to run our logistic model. So let's take a look at this data set. Again, it's from the ISLR data set. The name of this data set is S markets. So the variables stored in this data set include year, the lags, the volume, today, and directions. So it seems like it's pretty vague of what you are trying to do here, right? So, well, what are those lag? What are those directions variable? Well, if you want, you can always print a summary and try to see whether those numbers are or those variables are categoricals or maybe. In this case, well, most of them are actually the numericals. Except, of course, the directions here, we have up and downs and the counts of the two here. All right, so again, I would like to suggest you guys to keep practicing whenever you have the data sets pulled out from somewhere in the internet or maybe from the library. Try to practice saving it. And in this case, you can actually use this functions here called write.csv. This is a R function, so it's built into R, so you should be able to use it without any problem. If not, then try to find some resources online and see how to use this write.csv functions. Exactly the same thing happened here. You pass in the dataset name from your library, and you write the path to the directory you want to save this file, and you include the name of the files at the end. And you save it. The first column is the title, so you don't have to include it in your data. And you run it, and it's pretty quick. Well, as you can see, well, not only the size of the file matter, but the types of file that you are going to write into your machines also matter. Depends on the types of files. CSV, it's comma-separated vectors, so it's usually faster to save compared to the Excel formats. All right, so again, well, we want to know what is in this data set here. And for people who are trying to study finance analytics, this is the data sets that you most likely will encounter. In this data sets, again, it's coming from ISLR. It's the S&P stock market data. it gives you 1,250 observations on the following 9 variables, including year, which year of that observation is being recorded, the lag, which is the percentage change or the percent return for the previous date, and lag 2 is the percent return 2 days ago, and lag 3 is the percent return for 3 days previous, and so on. The volume represents the share of trades for that particular stocks on the current date. And today is the percentage change of percentage returns for the stock today. And directions. And direction only has 2 variables, which is up and down. It basically indicates whether the market is turning up or turning down. So if we have the markets going up, then it's a positive number. If it's going down, then it's going to be a negative returns on that given date. So the resources are coming from the S&P 500. This kind of market data, it's actually quite common to get from the finance operations. All right, so the first thing we want to do here is to look at the pair plots to kind of have a visuals of the correlations. So let's run this pairs functions. So again, the pairs functions allows you to plot all the variables within the data frame. So you are calling the data set out. So the data set has 9 variables in there. So it will plot all the directions. So you run the functions, and now it should actually give you the plots here. And as you can see, those are the correlations that you can actually observe from, let's say, lag 1 corresponding to lag 1, lag 1 corresponding to year, lag 2 corresponding to lag 4, today corresponding to lag 3, right, volumes. All right, so today our main goal for this analysis, just like any financial analysis that you imagine, is trying to use a statistic model to kind of predict whether the stock, given certain feature, will more likely to go up or down. And in this case, of course, you can actually imagine what are the related variables. So the lag obviously will be a very common way to include in our model, because what happened yesterday will influence how people invest on that stock on today's, how the second days before the today's trade will also make some kind of concern about how people should invest their money into certain stocks. So the lags definitely will give you an idea of how people follow the previous records of the stocks and determines whether they should buy in or buy out. The volumes should also be something we care about, because the volume will determine how frequent the stock will be traded. So in this logistic regression modeling, we are going to save the fits of the model into this glm.fit. Unlike the regression modeling, in the logistic modeling, we are going to use a different functions. We call this a GLM functions. So the GLM stands for General Linear Model. So it's a more general linear model you can use for various kind of distributions defined. For now, I would just make it very simple. Even the linear regression model that we've seen in chapter 3 can also be used by using the GLM models to get the outputs. But again, since a logistic model, it's not just a linear model. We are not trying to fit a regression line to a data point, but we are trying to model the probability of the odds whether the stock market is going to go up or down. So, or the stock is going to go up or down in given features. So in this model, we have the GLM functions. We put in, again, very similarly, the response variable first, we want to actually make a predictions on the directions. And then you want to use this squiggly lines to define what are the predictors for predicting the response variable. And in this case, we are going to include lag1 plus lag2, lag3, lag4, lag5, and the volume. Well, there's a little bit more things that you have to define in a logistic regression model. Instead, to define the data sets that you're going to use, there is one more thing that you have to define here, which is the distribution you are going to use for this logistic model. So just like how we learn it from the lecture videos, I think most of you guys understand now we are using the logistic functions to kind of model the probability whether the response variable will have a certain chance or certain odds to actually be either 1 or 0. So in this case, this binomial family distributions is going to allow us to run a predictions when the distribution described only with the response of two classes. So the term binomial basically giving you the chance of understanding the distribution only describes the chances or the odds whether one thing or the other thing that could happen. The terminology here, the binomial terminology, is a distribution that describes a choice of two. So either 0 or 1, or yes or no, or you go or not go. So it gives you that idea of why we are using this binomial distribution as our family to use. Now, if you run this model, let's run this. And pretty similarly to what we do with the linear regression model, we are going to print the summary of this GLM fit. And as you can see, you have, again, very similar outputs as you were getting from the linear regression model. So first of all, you are going to see how your model is being defined here. And then what you're seeing is all the coefficients that relate to the intercept, the coefficients with lag1, coefficient with lag2, and so on. The interpretations of the p-values, it's also the same as the previous we learned in the linear regression models. The smaller the p-value is, the more statistically significant it is. And we can also see how this model is being defined by the degree of freedoms. Well, what you don't see here is the R-square and also the F-test. The reason is because this logistic regression model does not, unlike the linear regression model, we are not trying to fit lines for the data point. We are trying to approximate or estimate the probability of Y could happen given some event of X's. So it's a different measures, and we will talk a little bit more about this measurements in the class. But for now, we just say, okay, we get some estimates, and unfortunately, all of them are not statistically significant. But today, objective is not just to get a significant result. We want to actually get more interpretations from this model here. Well, as we talk about in the video lecture, I think now you'd understand how to use this beta to make approximations of the probability or the odds when the Y is going to be equals to 1. So we're not going to go into the equations to do the math ourselves. Instead, we would like to actually ask R to do the math for us, because R can do this math fairly quick, of course, comparatively to what we did by hand. So in order to get the probability results, the predicted results, we can actually use the functions here, predict. And these functions will actually take the model that you just built, which is the GLM.fit model, and you can actually put in types, which is the response. And now if you store this predictions into glm.probs, this whole thing is going to save all the estimated probability or odds for every single observations that you pass into this model, so that you can actually see what are the probability related to each of the case in your data. Estimated. So let's run this. And I just store 1,250 estimates probability into this glm.probabilities. And let's first see the first rows of the results. Now, on the first 5 rows, we actually see the estimated probability. So for instance, the first observations we have when we pass in lag 1, lag 2, lag 3, until lag 5, and the volumes into our logistic model estimates, the betas will actually do the approximations, and the probability that turns out to be will be 50.70841% of a chance that y is going to equals to 1. So I think we defined here 1 is representing the stock market going, or not the stock market, but the stock itself is going to go up. If we take the second observations and put into our estimated models, the result will be 40.48146. So that means, well, approximately 48.146% of a chance that the stock will go up. And the third ones, the estimated probability is 48.11388% that will go up. And number 4, 51.522, and so on. Well, but the problem is we cannot actually look at this numbers and try to compare to the actual data, because the actual data only has 2 values, which is either up or down. It's not in terms of probability. It's basically defined by the category, the class. So if we want to actually change all these predicted results into the 2 classes so that we can actually check whether it match with our actual data. So what we can do is to define the thresholds. So in this case, we are going to use the if-else functions. So the if-else function basically tells us to define whether the variable will belong to which class by the defined conditions here. So in this case, we are putting in the conditions if the GLM estimated probability is greater than 0.5. So in this case, if the probability is over 50%, then we call this as a category up. We basically just insert a number or a text up to that particular result. However, if anything that it's not, GLM probability is not greater than 0.5, let's say equals to 0.5, or anything lower than 0.5, then we will put down as the result for this probability. And we are going to save this into what we call the glm.prep, which is the predictions. Let's take a look at this functions. So let's run this. And again, I store 1,250 results. And let's print the first 5. All right. So the first one, it's up. And again, why? Because our estimated result is 0.507841, which is greater than 0.5. The second result is down because, well, our predicted probability is less than 0.5. And the third one is down, the fourth one is up, the fifth one is up, which is according to our predicted model here. All right, so now we have actually turned our prediction into something that could possibly compare to the actual data. We are going to try to see if we can find the fits of this model. We want to know how well this model helps us to predict the category of up or downs in this data set. So we will attach stock markets data sets just to save some time, not to type too many things. And we are going to use table. And this time, the table function is used to create a table by passing in the GLM predicts and the directions from our data set. So what it does, it's basically putting the two side by side and compare it. And let's see how it looks like. So as you can see, in this table function, it puts the directions on the tops right here. The GLM predicts on the verticals. So it will tell you, hey, if the directions has a downs and the GLM predictions also has a downs, there are 155 of them are correctly predicted. On the other hand, when the stock markets or the stocks has a actual data that sets it up, the model also have 507 of this result that it's matching with the directions, which is the actual data. But what is unfortunate to see is when the actual data points showing up 141 and there are this many data point in your prediction that sets it down. So that means, well, this is a error. And when the actual data showing downs, there are 457 of those results in our estimates actually say up. So again, this is also an error. So what we are seeing here is this model can only predict this 145 and this 507 number of results correctly, but there are left with almost 600 data points that cannot be correctly placed in the right class. All right, so seems like a very convenient tool, right, to put everything into a table and trying to see it. But we also want to measure the accuracy of the table by creating the prediction tables that can actually take the means of the correct results. So we are going to use the mean functions here. So mean means average, and we are going to pass in the statement here where we want the means where the GLM predictions, and we have the equal sign, so it's basically the equals statement to the actual data directions. So we run this and we get this result. So this tells us on average the model can predict 52.16% of the results correctly. Again, the equal means, well, the predictions is equals to what is showing in the data set. So that's the average rate of accuracy. We can also check for the error, the average error of the model by reversing the methods. So we can use the mean functions here. We take the average, and then we are trying to pass in the statement here, where the GLM predictions, and as you can see, we have the very weird syntax here. We have the exclamation mark and equals. In computer science language, usually it means that it's not equals. So you will not see that mathematic notations because we cannot type that mathematic notation easily from our keyboards. So in terms of computer science language, we usually use the exclamation mark plus the equal sign to determine this is a not equals. And of course, we want to compare it to the directions. Now, let's see. As you can see, well, about 47.84% of the results from our model's predictions cannot be matched correctly to the actual data. So obviously, it's not a very good model to use. Well, which is kind of explained by the model itself. Because when you go back up and trying to take a look of the p-values of each of these coefficients, none of them are actually statistically significant. So that means we are building a model specification that is too complicated and including too many of this junk in our model and affecting the prediction results in this model. Now, for better accuracy, we are going to try to, or maybe to have a better sense of how accurate the model fits to our data. We are now trying to use methods to separate the data into two sets, and we call this a training set to train the model, and we will use a partial of our sample data as a testing set later to run the predictions so that we can actually see how well it fits to our models, to our data points. All right, so here what we are trying to do is to create a training set of data, and this training set will equals to the data S markets when year is less than 2005. So that means, well, in the data sets, we know it has the data from the year of 2001 to 2005. So that means, well, except for the year of 2005 data, we are including everything into this training data set. So we save it. And as you can see, well, we have the training here. And now what we want to do is to use the GLM model again. And we put in exactly the same specifications, directions. And the predictors are the lag 1 to lag 5 and volumes. We are going to use the S markets data sets and the binomial distributions. And this time we are going to use only the subset of data, which is the training sets that we define here. And after we run the models, we can actually try to print the results here. And it's always good to always see the result yourself. GLM fit. So in this case, obviously you are going to see different numbers for the coefficients and the p-value. Well, even though all of these are still statistically insignificant, but it doesn't matter. We're just trying to do a demo here. But as you can see, well, those numbers are different than the ones that we did earlier. All right, so what we want to do now is trying to make a predictions. And remember, what we want to do is to use the predict functions and pass in the model, use the model to run the predictions. And this time we have the new data, which is only the one that it's not belong to the training sets. Again, remember, we talk about the exclamation mark. The exclamation mark usually refer to not. So that means, well, we are trying to pass in a data set from S markets, which does not include the training sets that we use in our models. So the leftover basically is the year of 2005 data. And we set it as a response. Let's run this. And as you can see, well, we actually storing 252 results in this case. And we are going to do the same thing because we want to compare them to the actual data sets. So we are going to use the if-else functions and pass in this probability estimates. Whatever that has a probability greater than 0.5, then we label it as an up, and if not, then it will label it as a down. And we run this, and as you can see, we are storing 252 results from the year of 2005. So we're using the year of 2005 data to try to run the predictions. With the data that we model, with the data from 2001 to 2004. And now what we want to do, of course, is trying to compare the predictions with the test results. And we are saving this S markets directions, the actual data that's not in the training sets, into what we call directions.2005. As you can see, you have the up and downs, either 1 or 2, and it's now only have 252 that we store because it only includes the one that's not in the training sets, which is from year 2001 to 2004. Only contain the one that's in 2005. Now we're gonna do the table comparisons. All right, so in this case, when we're using our trained models to do the predictions, we have 77s down, 44 up. Those are the ones that's correctly predicted. And we have 97s that the data set is up, but the predicted model say down. And we have 33 that the actual data say down, but the actual model's estimates it sets up. So those are the results, and we are going to try to take a look at the accuracy rates. How accurate we are. Ooh, when we're using a subset of training data in our data sets and test it with the test data sets, we only get 48% approximately correct in our predictions. And now, when we run this with the error rates, and as you can see, we have a higher error rate comparing to the previous because now we are not including all the informations in the training model, but we are testing it with the unknowns data sets that we didn't train in 2005. So in this case, obviously, we are going to get a higher error rate. Well, this is something that we are going to learn a lot more in Chapter 5 to do validations of the model and see how this model will be used to do the predictions for unknown data. So we're going to talk a little bit more about the validations process later, but for now, I think it's a good time to kind of like just take a concept of why we are doing this. The main reason, of course, is trying to use some of the information from our data set and train it in our statistical model and test the unknown data, which is the one that we didn't pass into the model for approximations of the accuracy rate. Now, in the previous model, obviously, we found that LAC1 and LAC2s are probably the best predictors in our model, which makes sense. So we want to actually build a smaller model in this case in order to avoid putting too much noise and too much junk information into our model. So let's see if it improves. So this time we are going to have a better another fit by using the GLM models. And we pass in the directions again, our response variable. And this time we only include LAC1 and LAC2. We pass in the data sets, data equals to S markets, and we are going to use the binomial distributions for our model, and we will also specify we are going to only use the training data sets, which is the year of 2001 to 2004. So we're going to run this model, we save the model, and now you can actually use this to predict the probability with the testing sets. We are going to have 252 testing data because it's all the data we have in 2005. And we are going to make a predictions of the label by defining the probability of 0.5 or above will be up. Anything below 0.5 or equals to 0.5 will be down. So we save this. Now we are going to do the table. Wow, let's take a look at this result here. So the results here suggest we have 35 of the direction in the data sets down and we can correctly predict them in our models with 35 of them. And for the actual data that went up, we also has 106 of the estimations that can correctly predict the uptrends. But we still have some failure. In this case, we have the data represent ups. 35 of them are predicted as a down, and the actual data represent showing down, but the estimated the model's estimated result will say up. So there's still some error term. Obviously, we cannot actually always get 100% correct, and if it does, then well, obviously we are overfitting the models. But we can also check the accuracy rate here. And the accuracy rate in this case, it's 55.95238% correct. And the error rate in this case, it's basically 44.04762%. So significantly improve the results here, because this time we actually improved the accurately predict the result by almost 7%. Right? So previously we have the results here that we can accurately predict the results only about 48%. But in this new specification, by just including leg 1 and leg 2, our predictions result actually improved the accuracy rate by almost 7.9%, actually almost close to 8%. So that's very impressive. And also it reduced the error terms, the error rates significantly here. So for now, I would say, well, using the logistic model, it's not that difficult. But what is important to keep in mind is after you're running the model, you're getting those estimates, you want to actually try to find out whether the model is doing well or not doing well by using the comparison matrix and also the accuracy rate and error rate in order to determine whether the model has a good fit to our data. Unlike the linear regression models, in the linear regression model, we usually will look at the R-square and the significant level of the model, the significant level of the coefficients to determine whether it's a good model or not. But in a classification model, what's important to us is that we can actually correctly predict or maybe accurately estimate the final results that match with our data sets. So those are the things that we are going to learn more in the class, and hopefully this video actually helps you to grab some of this essence of the model so that you can use it in your assignments. All right, so it's almost time to end the video here, and I will talk about the linear discriminant analysis next time in the next videos, and also the quadratic discriminant analysis. Those are the interesting concepts to cover, and we will talk a little bit more in the class before we moving on to the cross-validations chapter in chapter 5. All right, so prepare yourself for these new models and trying to get the idea and practice with several data sets and see if you can use it for your own projects. I will see you next time. Have a nice day.